Hi guys, can you hear me? All right, let's get started. All right, so today we're going to continue talking about graphs. Last time we started out discussing connectivity and directed graphs. Then we transitioned into discussing paths. Okay, we were kind of moved on to look at a different combinatorial problem, which was starting from a start vertex. You want to find the distances from that start vertex to all other vertices. Okay, and we first looked at some sort of degenerate case where the distance between sort of any two vertices that are connected is always the same, 1. Okay, and we saw one particular algorithm that solves that problem. What was the name of the algorithm? Yeah, but you should also remember what it stands for, because it actually helps to remember what it is. It's breadth first search. The breadth there is that you're first looking at your own neighborhood, okay? Because you're kind of expanding this shell of these rings of farther and farther vertices from the start. So kind of you're first going in breadth as opposed to depth of search, where you kind of keep following deep and then you backtrack, okay? So what we're going to do today is we're going to look at the sort of general problem. Not fully general, but now we're going to allow distances to be different, okay? And we saw some sort of inefficient reduction between shortest paths with distances to shortest paths with unit distances. And that reduction, where you just insert a bunch of intermediate nodes, was inefficient. Okay, so we have to do something different than that. Okay, so that's kind of the plan for today. So today we're going to look at shortest paths with distances. All right, just to make sure that kind of this problem makes sense. So our input now, before it was just a graph G and kind of a start vertex V, right? But now we also have these distances. You can think about them as kind of they're living on the graph, though sometimes it is nice to kind of make them explicit. So we're going to have these lengths L. So it is just a labeling of the edges that assigns to every edge a number. And we'll start out with an algorithm that works where all lengths are strictly positive. Okay? What happens if they're 0? Well, you can just pre-process the graph and collapse vertices if you want. What happens if they're negative? We'll talk about it later. Okay? But so right now, let's assume that all lengths are positive. For simplicity, let's also assume that they're integers. Otherwise, you have precision issues. Okay? So there's the input and the output. We want to compute an array where we have distance. So for every vertex in the graph, we want to compute a number, which is the distance of, we're going to store in an array a number, which is the distance from S to V. Okay? So, by the way, whenever we talk about shortest paths, we're generally putting the emphasis on computing the length of the shortest path, though for pretty much all the algorithms that we're going to discuss, you can basically leave breadcrumbs along the way with back pointers, and you can actually recover the actual shortest path. Okay? Like which path has that length. Okay? So I'll point it out when we get there. Okay? So is the problem clear? So that's the problem we want to solve. Okay? By the way, what is this? Distance is just the mathematical definition among all paths from S to V as you sum up the contributions for the lengths. Okay? All right, so that's the problem we want to solve. Any questions here? Yes? The question is, are we assuming that a triangle inequality holds? For example, a graph that is planar would satisfy that. No, we're not assuming that. Okay? We're only assuming that lengths are positive. Otherwise, they're arbitrary. Okay? Good question. So we're going to take an approach. So by the way, for Deco, today we're going to discuss a rather important algorithm. The name is Dijkstra, after the person that invented it. The person in question actually made extensive contributions to programming languages and graph algorithms, and for that he was awarded the Turing Award in the 70s. It's a somewhat non-trivial algorithm, but there is some sort of intuition that takes you from BFS to Dijkstra's algorithm. And the intuition that carries over is that you want to kind of grow a region of vertices for which you have figured out the shortest paths. So the base case is kind of simple. You start, you know something, right? At the start, the shortest path from the start to the start is 0, because the base case is fine. You want somehow inductively to say, well, if I figured out all the shortest paths within a certain region, I would like to make one progress. Like, I want to get one new vertex where now I know the shortest path for that one. I can grow my region a little bit, okay? So it's just about balancing what is the induction hypothesis for growing this region in a way that we know what to do, okay? That's kind of the high-level intuition, which is the same as BFS, right? We're kind of growing this region where you know where things are, okay? So the state of the algorithm, just to make this a little bit more precise, will consist of two things. First, we'll have the working sort of best estimates of distances for all the vertices. So we're going to have an array where for all the vertices, we're going to have some distance, okay? So at the end of the algorithm, this will literally be the correct answer, but halfway through the algorithm, it will be some estimate. By estimate, I mean it is literally the length of some path that goes from the start to that vertex, okay? So it's always at least as good as the answer. It will never be below it. And as the algorithm runs, these kind of distances will kind of settle into the correct answers, the shortest paths, okay? So that's one state of the algorithm. We'll also maintain a subset of vertices. Let's call it K for known, okay? English is funny, right? So K for known. And for every vertex in this known region, it will actually be the case that the distance, the number that we store in this array, really is the distance from S to V. Okay, so sorry, I meant to say state applies to both of these things. We have the estimates. Okay, so this is kind of the state of the algorithm. At any moment in time, it has all these estimates, and it remembers these are the things that I know. Okay, that kind of by design I know they are already correct. Yes. The question is, why do we need K? Well, the algorithm will need it because it wants it, and we'll get to it in a moment. I'm just telling you before we get to the algorithm, because if I just write the algorithm, it's going to be too much, okay? I'm trying to describe kind of how the algorithm will reason. It will reason as follows. It has estimates, and out of these estimates, it knows which are correct, okay? It's important that why does it know? Because mathematically we show some properties, some invariants, so the algorithm actually makes choices so that when it grows K, it knows that at that point, for everything in K, including a new thing it added, the estimate is correct. Okay, so there's going to be an invariant that we're going to try to maintain, okay, about this state. It is the following, that, well, I already wrote it, sorry. So this is the one here. No, never mind, with the invariant. So let's start with the base case. So the base case looks pretty simple, right? So we have this, all the vertices. Here they are. And we know at the very beginning, we can just think of the region of known answers K to be the singleton that is the start vertex. Okay? Now, as you will see in a moment, the algorithm actually will not only reason about k, but will reason about k plus a little bit. Okay? These will be called edge extensions. It's basically k plus all one steps you can take outside of it. Okay? So you might have some neighbors that are just one step away from k. All right? So in this case, we have k is s. Okay? And there will be some property about the estimates there. So now let's get to the induction hypothesis, or at least to the kind of inductive step. Let's try to derive how the algorithm should reason. Okay? So again, we have all the vertices. Here they are. Now we've gone through the algorithm that we haven't designed yet, but there is some state. Here it is, of known vertices. Now, because they're known vertices inside of it, we actually know all the shortest paths. So we have an S. Here it is. And we have paths to things. So here, for example, a shortest path. Here is to this and that one. Right? So it will look like that. By the way, now we're going to prove it here, but all shortest paths form a tree. Right? Hopefully that is clear to you. Okay? So here's the tree of shortest paths that we know so far. Now, by the invariant, we'll know that for each of those, this holds. And now we're wondering, okay, well, all of these guys, they have friends that are one hop away outside the region. And we're wondering, okay, we need to make progress. It would be nice to enlarge the known region by one vertex. If we can get that, then we have to just repeat v times, we'll be done, right? And we should think about which of the things outside of k is a good candidate to make progress. First, let me say that things that are far out, like somebody here, is probably not a good candidate, right? It's just out there. It's far away from the things that we know. So let's just kind of discard it. Those are not good candidates to make progress on. Okay? We're going to instead try to understand some mathematical structure about these vertices that are outside of k, but they're reachable in one step. Okay? So now we're going to prove a lemma, okay, that will tell us that if we know the shortest paths inside of k, then one out of these edge extensions must be itself a shortest path. And there is a way to identify it. Okay? So let me say it again. We're going to prove, first mathematically, that out of all of these guys that are one hop away from k, one of it, say this one, is such that this is its shortest path. Therefore, what we can do is to tell the algorithm, well, here's how you grow k, and then repeat. Okay? So there are two things we need to do. We need to clarify ourselves why one of these should be a shortest path. Okay? And then second, how do we identify it? Okay? Because the algorithm really should pick one of them. There might be multiple, right? That's the plan. Okay? So let's look at let's give a name to let's give a name to this one. Let's call it A. Okay. So who is that guy? Okay. So let's say here how to extend. Okay. All right. So let's look at an arbitrary shortest path that goes from S to A. And now we're going to look not at just any A, but we're going to set A to be the vertex in V minus K. So this is anything that is not in K that is closest to S. we're just reasoning right now. I don't have shortest paths yet. So I actually don't know who is this guy. But you will agree with me that provided that k is not equal to v yet, we have some vertices outside, right? All of them have a distance that is well defined to S. One of them will be closest. Okay? Fine. So now I want to argue, claim, A is a one-edge extension from K. So now we're saying we define A to be the closest to S outside of K, and now we want to claim that it must be one out of those up there. Why? Well, let's see. Look, there is a path, a shortest path from S to A. This shortest path starts in K and ends outside of K. It must cross the boundary of K, say the first time. Okay? Somewhere here. Okay? So that's the boundary of K. Okay, so there is a last vertex inside of K. Let's call it B. All right? Now notice that, or rather, there is a first vertex outside of K. Let's call it B. Now, if B equals A, we're done. Right? That's what we wanted. Right? But if B is not equal to A, right, this is kind of, we can reason by contradiction. Suppose this is not the case. That means that A is more than one edge extension. So let B be the first one on this path that is outside of K. But look, we have assumed that all lengths are positive. So it means that, here there might be other vertices, but this path will be positive, right? So it means that B actually is the closest one to S, not A. That kind of contradicts our choice of A, right? So we were correct in assuming that A is a one-edge extension. So this picture cannot hold. The correct picture is that if you pick the shortest path to A, then K is exactly here. It is the first one to be outside. Right? Are we comfortable? Again, we're saying, suppose this is not the case. Well, then it means that pick the shortest path from S to A. There will be a first one outside of K. Let's call it B. It is before A. We have positive lengths, so B is closest to A, closest to S than A is. And that's not okay, because we picked A to be the closest one. All right, so now we know that actually out of all of those, there will be one that actually is a shortest path. Okay? But we don't know the shortest paths, right? We only have estimates. Do you have any suggestions about how we should be picking, how are we going to identify which of those is A? Yeah.
So if you look at all of those guys that are one edge away from K, you should pick the one that minimizes the edge length outside K plus the known distance to its neighbor inside K.
All right, so good. So it's a good suggestion. Let me repeat it. So let me switch the boards. All right, so the suggestion is as follows. Look, the algorithm already knows literally the distance between anything in K and S, right? So we have this distance, we have this distance, we have this distance, we have this one, all of these, right? Now, we could just see and say, look, let's just consider one by one each of these. Try to add the length of the path that crosses the boundary and pick the one that is closest. Why? Because look, the shortest path will not be longer than that, right? Because it's the shortest path, okay? And if we pick the one that is closest, okay, we're guaranteed that that one is going to be the shortest path to it, okay? Let me say it again. The algorithm will maintain, by the way, also, this picture is a little bit slightly degenerate. Let me make it slightly more interesting. This one edge extension could be a one edge extension both of this one and of this, for instance, right? Maybe that's another way to get there, right? So whenever we are considering this one, we should not only consider the length of this path plus this one, we should also consider length of this path plus this one, okay? And consider those are as valid estimates for this one. Of course, we're only interested in the smaller one of the two. But out of all the estimates that we have for the one-edge extensions, we will pick the smallest one, okay? That one is guaranteed to be A, okay? Right, so while you think about it, I'm going to write the kind of pseudocode for this algorithm so that whatever I said becomes more concrete, okay? This is a pretty tricky algorithm. So in the algorithm, we're going to start out by putting the estimate for S to be 0, and we're going to put the estimates for everything else to be infinite. Okay? We're going to start out our known region to be either S, or in fact, in this case, it's easier to think about it as empty. Okay? And while the known region is not everything, we're going to do something. Okay? What is that something? We're going to pick some vertex V outside, okay, with smallest estimate. Notice that the first time that we are running this algorithm, all of the estimates are infinity, so we'll definitely pick S. Okay, because 0 is less than infinity. And then we're going to add V to K. Okay, so this is the one that we picked and we put in, right? But once we put it in, kind of the boundary of our edge extensions changes, right? Because when we have added A, maybe A contributes some, let me write them dashed, some new edge extensions, or maybe contributes to information about previous edge extensions. So we have to go back and revise estimates, either from infinity to something finite, as in this case, or from something finite to something possibly smaller, as in this case. If this is a worse path, then we're not going to substitute it, right? So that's why after this line, we should be doing precisely that. We're going to say, for all outgoing edges from V, the vertex we just added to the known region, we are going to make a comparison. If the distance that we have for the edge, for the sort of the other side of the edge, so we were going from V to W, if the current estimate of W is bigger than what we would get from distance of V plus the length VW, then we're going to set our estimate for W to be this value. Okay? Because we have a better estimate to get there. Okay? So is it clear, this algorithm? captures what we just discussed. We're picking the one that has the smallest estimate, okay? By the way, why is it an edge extension? Because, look, the things we haven't touched yet are infinity, right? And so the things that have a finite dist value are either already inside K or a one-edge extension, okay? So this line is basically saying, look at all of these one-edge extensions and pick the smallest one. Once we've picked it, the reasoning that we made tells us that it's safe to add it to K. And at this point, dist V is correct. But now, because V is now part of the known region, we have to readjust our boundary, okay? And so the new information brought by V is in the form of its neighbors. So we go over all of the neighbors, and we say, okay, well, through V, can you get there in a better way? If so, let's update the estimate. And otherwise, we'll just leave it as is. You go there through a different neighbor. Okay, so through some other vertex, okay? Now, this algorithm is not completely specified. We'll come back to it in a moment, but I want to kind of pause for a moment and ask, is the specification of the algorithm clear? There's some issues about how we implement it. We'll come to it in a moment, but at least as, I guess, pseudocode, should be clear. Yes? Can you speak louder, please? Peak. Oh, I'm sorry. This is all vertices minus the known region. This is set difference. Okay? So all the vertices minus the known region. So just pick something in the complement of K. Yes? So the question was, how do I know that the edge extension gives me the path? Okay. So it's again because of this argument that we just argued that not only, let's put it like this. When we made this argument for this K, we know that actually this one will appear among our choices. Because A is a one-edge extension, it means that this particular one will be one of those that we consider among all options up there. Right? Okay. Again, the question was, how do I know that among all the ones that I consider, not only I will pick an A, but that is the correct one, but the value I set for it corresponds to the shortest path. Okay? The answer is that because this is this being on the shortest path to A, is one of the options that I will consider. Okay? It's a good question. But there are indeed two aspects here to argue for the correctness of the algorithm. One is that you pick the right A. Secondly, when you put it inside K, you have set the distance of A to be the correct one, because we don't come back to it later. Okay? I can say it 10 times, but it will still be confusing. At some point, you will sit into a dark corner and reason it by yourself, right? Yeah. W is not quite similar to A. The analogy between here and this picture is that A here is V. We've decided to put A inside K. And having decided that, we have to redraw K. And A gives us new vertices, which we need to account for. And that's what we're doing here. Okay? Good. All right. So now let's spend a few minutes discussing how this algorithm can be efficiently implemented. So notice that as this algorithm goes from iteration to iteration, we're kind of changing the estimates. And so the relative order between the things that are left over in the complement of k also changes, right? So we need a data structure that will let us do certain operations efficiently, maintaining this kind of set of elements that for which we are able to update their value, and we're still able to pick the minimum one out, okay? So I'm not sure in which class you may have seen this, but this is exactly where you would use a priority queue. So let me just spell out slightly more precisely how the priority queue kind of API fits inside this kind of abstract pseudocode, okay? So the first thing we're going to do is we're going to negate the logic, okay? Instead of starting with an empty known set, we're going to start with a full unknown set, okay? So here, instead of k being empty, I say, okay, u for unknown, please start to be everything, okay? So that's one change. Now my while loop, instead of stopping when my known region is everything, it will stop when my unknown region is nothing, right? So I'm going to cross this out also, and I replace it by saying u not equal to empty set. All right? Fine. So now we have this thing. It says pick the smallest. Well, now in V subtract q, that's just u, right? Okay, so pick the smallest element in u. Okay, but that's just the, I don't know how it's usually called, but it's delete mean, right? So we have the q. It's still represented by u, okay? And we're going to delete it, and it gives us back v, okay? By the way, up here, I guess you can also think about this as make q, right? I'm not going to keep writing the UE because it's just annoying. So with v, sorry. You say, please make a q with v, and the distances, right? And it will return back your q, which I'm identifying with the set u. Okay? Here you're going to say, please delete mean. It will knock out the smallest v from the q. All right? And that's now you have it in your hand, right? The only other thing that we need to do to operate on this queue is to be able to change values, okay? So that would be kind of this line over here, where after we compute this value, or at least if we did our over here, then we just add a line that says decrease key. And then we're passing in the q and the value. I don't know how to call it, alpha. Okay, so that value that you want to change. Okay, so the kind of data structure operations are decrease key, delete mean, and make q at the beginning. Okay. Again, all we've done is we've negated the logic, and we have just made explicit what is the kind of portfolio of function calls that we need to realize this algorithm, right? Yeah? So decrease, again, I'm not sure where you've learned priority queues and what names you're familiar with them, but when you do a priority queue, you kind of stash a bunch of elements into the queue, but they all have so-called keys or values associated with them. So this is a function call that says, hey, Q, please decrease. So I forgot to put the other argument. Please decrease for the element W, which is the one that we're changing, set its key to be some smaller number, alpha. Okay? All right. Okay, so it looks a bit messy, but hopefully, sort of the incremental sort of changes that we did, they're clear. So now that we have an actual data structure underneath, or at least something more concrete, we can try to think about what is the running time of this algorithm, okay? So let's think about the runtime. Now, because we have a data structure, we really should be counting how many invocations of each function we make, right? So we have a make queue at the beginning, right, which you can think about it as just v inserts, right? Just like put in. Notice that you're doing something, right, because you're putting them in and they have values associated with it. When you're done, this should be a priority queue, right? So it is aware about the values of all the elements. How many delete mean we're going to do? V, right? Because once we take something out, we never put it back, right? Because it's now part of the known region, or we took it out of the unknown region, okay? So we have V delete min, okay? How many decrease keys do we do? Total. I heard a V. Maybe we need something a bit more precise. So if it's not V, it must be E, right? Because when do we ever even consider doing a decrease key? Well, whenever we consider the edge VW, we may consider to decrease key on W. But each edge, we consider it only once. One direction, maybe the other, but overall it's size of E, right? So that's the worst case. We are making size of E decrease keys. And usually less, right? So we have size of E decrease keys. Now, the fact that we have a data structure and we're counting data structure function calls doesn't mean this is all that's happening, though in this algorithm it actually is, right? So the running time is dominated by these operations. So then we should decide where the priority queue comes from, because how it is realized as a data structure will determine the cost of each of these different operations. And it will give whatever weight you put on each of these and you add it up will give you a different running time, right? And again, this is not a data structure course, and I'll just say that there is a choice of priority queue, for example, a binary heap that we're not covering. You can look it up yourself if you want, where all of these have worst case cost that is log size of V, okay, size of the queue. All right? So this means that overall, the cost of this algorithm is going to be what? So we have V inserts, V delete means, E decrease keys, and each of these costs log V. So, right, so we're going to have V plus E, everything times log V. Okay? So it is not quite linear time, like BFS. It is a little bit slower. Okay? We have this logarithmic overhead, and is brought about by the fact that we're using a priority queue, which is a more sophisticated data structure, rather than just a queue, which is what we were using in BFS, for example. Okay? But it's still pretty fast, right? I mean, if you think about kind of the kinds of algorithms you might have thought, maybe it would have been a lot slower. This algorithm is remarkably fast for finding shortest paths. Now, for each of these algorithms, especially the slightly more complex ones like this one, it's always great to go through some example and kind of keep state and do some bookkeeping. I'm not going to do it for this one. Otherwise, we're just not going to keep moving in these lectures, OK? It's going to take 10 minutes to go through an example. I just encourage you to kind of pick an example, maintain dist and the state, OK? And just work through it to make sure that you see what's happening and kind of you feel the progress of the algorithm, OK? So I have it here on my notes, but I actually don't want to go through it. I want to keep moving. OK, what I want to talk about next is, so actually before I transition, more questions about this? Maybe another thing you want to do is maybe remember what is a binary heap. You will not need it in this course, we'll just make this algorithm less magic, because we are assuming something, some data structure underneath. OK, so what I want to do now is come back here, and I want to ask the question of what happens if the lengths are not positive, OK? So if we have some negative lengths, kind of, why not ask the question there, OK? So let's do that. So the case of negative edges. So question, does it make sense to talk about shortest paths with negative edges? Yes, no, oh, maybe. Why no? Why yes? Okay, so one remark is if you have a negative cycle, it doesn't make sense. Yeah, I agree. So what is a negative cycle first and foremost? So let's say that you have a graph that looks like this, and you have, I don't know, 2, 1, minus 3, 1 again, and then you have, I don't know, 2 again. If you notice, kind of this particular path, and if you add up all the contributions, and you go around it once, it has total kind of weight minus 1. So what is the shortest path from A to B? Well, it is kind of ill-defined, because if you just take this path, it will cost you 5. If you go around the loop once, it will cost you less, right, which is 3, right? If you go around it again, one more time, it will cost you 2. So there is no answer. So it is ill-defined. So ill-defined with negative cycles. But notice that if there are negative edges, it doesn't mean that there are negative cycles, right? If there are no negative cycles, then the question is well-defined. So really, we should restrict our attention to graphs that for now we're just going to take as a given. There's no negative cycle, and then later we'll see how we could detect whether there is a negative cycle or not, right? So now we're going to sort of look at graphs without negative cycles. Okay? So now we have, again, it's good to check these things, right? You don't want to try to solve problems that are ill-defined, right? But now it is well-defined. So we can ask the question again. So, all right. But now we immediately have an issue, because not only before we didn't have negative cycles, the fact that all lengths were positive was kind of crucial, right? We had this argument that I know how to pick the next vertex to increase my known region because I could argue that it is a one-edge extension. And to argue that it is a one-edge extension relied on the fact that a kind of on a shortest path, intermediate nodes are closer to the start vertex than the end of the shortest path. That's not true anymore. So let me write it here. So now let's say that we look at. So I think now I'm not going to need this anymore. So if we look at this graph, C, B. Oh, let's say here we have, I don't know, 10, 100, and minus 99. Okay? So notice that first there is no negative cycle. In fact, there's no cycle. Now the shortest path from A to C is this one over here, right? So you can go from A to C in length 1, right? Before, we had the property that if you pick a shortest path and you kind of inspect what happens along the way, for example, you find the vertex B, that's like what that is a vertex on the shortest path from A to C, we would expect B to be closer to A than C is. That is not true anymore because the distance from B to A is 100. Okay? So somehow, as you move down the tree of shortest paths, you don't have any more this, you get farther and farther away from the start. Okay, it's not true. And somehow that was like really crucial for the reasoning behind Dijkstra's algorithm. Wait, sad face, right? What are we going to do? So actually, it's pretty surprising that one can do something rather non-trivial. And the idea is to focus on the behavior of so-called update subroutine of Dijkstra, which is this one over here, okay? So I want to tell you a little bit about this update subroutine that has some nice properties. And once we understand these properties, we will be able to rather easily to come up with an algorithm. In fact, I think even simpler than Dijkstra's algorithm to solve the question. Yeah?
Can't you just take add the absolute value of the most negative weight for all the edges, and then they all become negative?
The question is, why not just shift everything up? Okay? So I'll leave it as an exercise. There's a counterexample to that. Okay. Yeah. In particular, maybe one way to see it is that if you shift everything up in the one with a negative cycle, it goes from a question that makes no sense to a question that does make sense, and that should give you pause, right? But that is a reasonable thing to think about. You should try to reduce to problems you already solved. Okay, so let's talk about the update procedure. So we're going to define update. This thing is of VW to be those two lines. So let me just rewrite them. You're going to set the distance of V UV. You're going to set the distance of V to be the minimum between, well, the distance of v or the distance of u plus the length of the path of the edge from u to v. Okay, so I'm just kind of putting down a macro. Okay, that says whenever I say update the edge uv, right? There's a direction here. That's not. I'm just saying it's not a symmetric thing. I'm looking at a specific edge. This is what you're doing. All right. So the first observation is that update is so-called safe. Namely, we could start with distance 0 on S and infinity on everything, and I could just close my eyes and start updating vertices for all you know at random, arbitrarily, in whichever order. And it will always be the case that distances can't get shorter than shortest paths. Okay? I can't mess it up. It's just a matter of like, how soon will I get there? Right? Or will I get there because I keep choosing the same edge all the time? Right? But the point is like, you can't mess up things so badly. So another way to say it is that provided that the distance of u is at least the correct answer, which is the distance from S to u, and the estimated distance for v is also not already wrong, then it says that after the update, kind of the new distance of v is also no worse than the correct answer. Okay? This is relevant because at the very start, I start with estimates, and all of them are above the correct answer. Because one of them is correct, 0 is greater than or equal to 0, and for all the others, infinity is greater than or equal to whatever is the answer. Okay? So this is what update is safe. Okay? So you can just go and update vertices. Now, the second point is that there is a condition that determines when you do an update and actually you get the right answer. Okay? So first I'm going to write something that is slightly wrong. I want to write it first. I want to say that it may look like a right thing to write, but it's incorrect. So I'm going to say if distance of u is correct, then update run on a u and v makes dist of v, I think like writes awfully, correct. All right, so I wrote a statement. It says, suppose for a moment that I know, for whatever reason, that distance of u is already correct, equals d of s comma u. And I happen to run update on the edge u comma v. Is it or not the case that after the update is run, the distance of v is also correct? So in Dijkstra, this was the case, right? In fact, we use this pretty strongly. And this really comes from the fact that for positive distances, you expect this to be the case. Okay? Does it make sense? But this is not okay in the case of negative cycles. I'm not going to try to come up with a counterexample. It's not difficult. But it pushes you in the right direction. There is like a related property that does work. Okay, and that's the one that we should keep in mind. Right? I'm wondering where to write it. Let me write it up here. So I'm going to write here wrong. Okay? And here I'm going to write a different 2, okay, which is the property that does hold. So if I write it in English, I'll write like a long sentence. I'm going to use a picture. So pick a shortest path from S to V. Okay, that's the shortest path. And now, look, on this shortest path, there will be a second to last node. Give it a name, U. Okay? So U is the second to last node. So just one before V in its shortest path. Whose shortest path? V's. Maybe this is not U's shortest path. Okay? Then, and the distance of U is correct. Then running update UV makes distance of V correct. Kind of almost by definition, really, right? Because what is the correct distance of V? Well, if this is the shortest path, that's our assumption. It is this plus that, right? And this quantity can be no greater than whatever we have already estimated for V. Okay? So whenever we run update UV, it will either leave it the same, so it was already correct, certainly leaving it unchanged makes it correct, or it was greater than that, and then it changes it to the correct value. Okay? So this is just a slightly more elaborate condition that says, when are we getting a correct answer by running update? Okay? But then we wonder, okay, fine, so that's a nice hypothesis, but how the hell do I know when this hypothesis holds, right? Yeah?
What was the extra condition you needed in the second statement?
Here? So this picture means if U is the second to last vertex on the shortest path from S to V, okay? And moreover, the second condition says, for whatever reason, the estimate for U is already correct, then, conclusion, if you run update on the edge UV, after the update, the estimate for V is correct. Again, this is almost a tautology, because what is the correct answer for V? It is, because this is the shortest path, this length plus this one. That's exactly what update UV will do. Okay? So, but this elaborate condition, kind of, on the one hand, seems a bit hopeless, because how do I know what are shortest paths? So, and how do I know that I will ever kind of find myself in that place? Well, that condition immediately gives a next step, an interesting next idea, which is as follows. So I need to keep track of time. So let's again consider a shortest path from S to V. Okay, so that's the shortest path from S to V. Now suppose that I'm doing updates on edges. Okay, and for now I'm kind of blindly doing that. So I do kind of update edge 1, update, by edge 1, not necessarily this one. So let's call it, I don't know, edge 7, update edge 15, update edge 3, and I'm just doing updates, okay? And some of these edges, I don't know, maybe edge 7 is here, edge 15 is here, okay, so that's 7, somewhere else in the graph, that's 15. Then it ends up being, I don't know, 3, okay? So this is edge 3. Not the lengths, the edges, okay? Now here's an observation. Now consider this sequence, okay? It's ordered, okay? So this is a sequence of updates that I'm doing for whatever reason. If as a subsequence of this sequence, I find these in order, I want to claim that then we will have a correct answer on V. Okay? So consider a sequence of updates. We're about to design an algorithm. What will the algorithm do? It will just update edges one after the other until it thinks it's done. So now we're trying to figure out what should the algorithm look like. Well, whatever algorithm it's going to be, it's going to update edges in some order, right? So just write down an order for a moment abstractly to think about, what should the algorithm do? I want to claim that in whatever order you write down, if as a subsequence you can find all these edges, so let's give a name to them. I already kind of named them a little bit, but let's call them alpha, beta, gamma, so on and so forth. You have update alpha as, the third in the sequence. Then update beta, and so on and so forth. I claim that by the time you go through all of these updates, you will have the correct answer on V. Why? Because update alpha will make sure that this guy has the correct answer. Okay? Update beta will make sure that given that alpha has the correct answer, once you run update beta, we'll get here the correct answer by this property. In the meantime, other shit can happen, right? You're going to update, maybe alpha again, or maybe update gamma actually before you update beta, but it doesn't matter. Update is safe, right? So because you're doing these things in sequence, you know that as you proceed in sequence, this gets correct, then this gets correct, and you have kind of this effect that brings you to the correct answer here eventually. Okay? So we said update is safe, so you can do things kind of willy-nilly. But now we're saying something slightly more refined. We're saying in any sequence of updates, if as a subsequence there is a shortest path, then you will have at the end of that sequence the correct answer for things on the shortest path. So this actually gives basically immediately an algorithm. Okay? What is the algorithm that I should run? Like, what is the intuition I want? I want an algorithm that whenever it's done executing, it has done a sequence of updates, and I can find, as a subsequence of this sequence, every shortest path. Right? Because if an algorithm has done whatever updates, and as a subsequence for every shortest path, I can find that path as a subsequence of this sequence, I will be done. Right? Yeah? So the suggestion was can we do BFS from S? So I can't come up with a counterexample on the fly, but the issue is that BFS may not consider all sequences. There might be sequences that are sort of kind of not ring-like in the way that BFS reasons. Right? It could be the shortest path goes like very far and then comes back.
So consider any shortest path. The first edge is between S and someone, right? And that's going to be the first level of guys that you're looking at in our BFS. So those updates will be run before any update from any other vertex will be run.
Yeah, but it may not be a shortest path until later, right? Like, I could have like an expensive edge to somebody nearby here, and only later I'm also not quite necessarily sure what do we mean specifically by BFS, because BFS is a precise thing, right? It says use a queue, right, and expand, and certainly that one will miss some shortest paths. But here's one idea, okay? Suppose that I go through all the edges in some arbitrary order and update all of them. And then, you know what? I do it again. in the same order. I do it again. I do it again. How many times do I need to do it to make sure that in the long list of updates I have every subsequence? How long can a path be? A shortest path. V, right? So I know that any shortest path will have length at most V. So now I'm kind of updating every edge repeatedly. How many times do I need to repeatedly do this such that I have every subsequence? V times, right? Think about it. Now I'm going to draw a table. I'm going to update every edge, update every edge again, update every edge again. I get a big table, right? E updates, V lines. I can find any subsequence in it, right? So let me just draw it. So this is an algorithm, has a name. It's called the Bellman-Ford algorithm, after the people that designed it. So let me first draw the picture for the algorithm, and then the code is actually exceedingly simple. So the picture you should have in mind is that you kind of plot you write out in a sort of imaginary table all of the edges, and you say, OK, update. So I'm going to shorten it to UD. Update E1, update E2, update E3. So that is the first kind of loop of my algorithm, OK? And I've done it once. Now I do it twice. Update E1 again, update E2 again, update E3 again. And I do this V times, or in fact, more precisely, I only need to do this V minus 1 times, right? Because in every path has at most V vertices in it. That means V minus 1 edges. So now look, I have a shortest path in mind, this one. And I want it to be present in the sequence of updates I've done. Well, this guy will appear somewhere here in the first list. The second one will appear somewhere in the second one, and it has been updated after that one. OK? The third one will appear somewhere in the third list. So kind of you can zigzag your way down, and so that preserves the order in which things were updated, and you can find every path as a subsequence of these. All right? So let me write it in code. So Bellman-Ford, we're going to start out our distances for S to be 0, and for the rest of V minus S to be infinity, like before. And then we're just going to have 2 for loops. First, for I going from 1 to V minus 1. So this is the number of outer repetitions. And then, for each of those times, we consider for all edges in the edge set, we're going to update E. OK? So this inner loop is each row here, and the outer loop are so each inner loop is a column, not a column, it's a cell, right? And the outer loop is taking you down the rows. OK, it's a very simple algorithm. OK, what is the running time? A little bit more than V squared. It is V times E, right? Because the one loop is V, and the other loop is E, right? So the running time of Bellman-Ford is order of V times E. OK? It's pretty direct accounting. Notice that it is significantly slower than Dijkstra. We're also solving a harder problem, so that's okay maybe, right? But yeah, now we can actually come back and think of Dijkstra. Dijkstra was basically a trimmed down Bellman-Ford. We knew through the structure of graphs with positive lengths in which order I should update edges so that I get answers correct earlier rather than later. Here, it's like you're fumbling. You know that after enough number of iterations, you've got to have all of the paths as a subsequence, so you just do enough iterations to get there, okay? And just we know that there's just not that many iterations in the worst case. In Dijkstra, we were choosing a very particular order of updates so that we have to do fewer updates in total. And the priority queue was kind of our guide for what is the next smart choice of update. Okay? Now, also for Bellman-Ford, and we could go through an example. I encourage you to go through it yourself. When you kind of compute it on a table, just remember that technically you're keeping track of like a 3D table, right? There is like, you have two loops and you have time, right? So whenever you kind of keep track of the state of Bellman-Ford in kind of your bookkeeping on a piece of paper, remember that in every iteration you have to update every edge, okay? So you may revisit the same vertex multiple times because you consider different neighbors, right? And so in each iteration, you might be updating dist multiple times. So it's not that you touch dist of v once in an iteration of the algorithm, right? You may touch it multiple times because multiple vertices may touch the same vertex. And that's just one iteration, okay? And you just do it again and again and again. So just really what I wanted to say is that I find it more complicated to keep track of what happens in Bellman-Ford, even though it is a simpler algorithm, than, say, in Dijkstra. Okay? Dijkstra is kind of much more apparent where you are in the algorithm in your head as you're kind of keeping track of it. Okay? Just on a piece of paper, Bellman-Ford is a little bit trickier, even though the code is simpler because of the loop, the extra loop. Okay? So I encourage you to kind of become familiar with it so, on a piece of paper so you don't get confused when it matters. Okay, so we're almost done with our journey of shortest paths. There is still a question that we haven't really answered. How do we know if there is a negative cycle, right? So, some of the graph will announce when it shows up as an input to the algorithm. By the way, I have a negative cycle. In a graph that looks like this, the cycle that is negative is obvious. But when you have like a messy graph, who knows? It might just be some weird grand tour that happens to sum up to something negative. So next time, we'll look at how we detect negative cycles. We'll also look at how we deduce shortest paths on DAGs, which is another nice class. And then we'll kind of move on to other things from there.